the last lecture, we saw how the symmetry of a crystal structure plays a crucial role in determining the behavior of solids, in particular crystalline solids and condensed matter in general. So, the elucidation of the crystal structure, namely the determination of the spatial position of the various atoms and molecules which go to make up a given solid, is the first important step in understanding phenomena in the solid state. Until the discovery of X-ray diffraction by crystalline solids, this was not possible, but the advent of X-ray diffraction by a crystalline solid, which serves as a 3-dimensional grating for the X-rays, revolutionized the situation and enabled a detailed mapping of the atomic and molecular positions inside a solid. Most of the phenomena in condensed matter take place under the influence of applied electric and magnetic fields, or through the scattering of particles such as electrons, neutrons, protons, etc., as well as elementary excitations such as photons, phonons, magnons, polarons, plasmons, etc., by the atoms and molecules in the medium. So, these are all scattering events which can also be used to reveal the details regarding crystal structure, spin arrangement, etc., in condensed matter, as well as to find to determine the normal modes of these excitations. This is the case, for example, in X-ray, electron or neutron diffraction, or in Raman, Brillouin, or inelastic neutron scattering. In this lecture, we describe the basic concepts which are common to these phenomena and examine some of their applications to the study of solids and liquids. In order to do this, we have to formulate the theory of what happens when X-rays are diffracted by a crystalline solid. We consider a perfect crystal which consists of a regular lattice of discrete atoms and molecules. When an atom is excited by an electromagnetic wave, it re-radiates this wave in all directions in phase with the initial excitation of that atom. This is just a consequence of what Huygens postulated in wave optics much earlier. The amplitude of the beam, X-ray beam, in any direction is obtained by summing up the contribution in that direction from each atom, taking into account the phase differences between these atoms. This figure shows the direction of the incident and diffracted waves for an arbitrary angle of incidence on a lattice of discrete atoms. So, we have a lattice which is shown by the heavy dots. So, those are the atoms, and you have a pair of a set of parallel crystal planes, and then the incident X-ray beam is scattered by an atom, for example, at B. The incident wave from A is scattered by the atom at B into a direction marked as C in this figure. So, that is the basic scattering or diffraction event. We all know from elementary discussions, which I do not propose to go into, this is based on finding this amplitude and finding the condition for constructive interference of the scattered or diffracted amplitudes. So, diffraction is known to occur when the waves reinforce each other, that is what I meant by constructive interference. The condition for a diffraction maximum is given by the so called famous Bragg law of X-ray diffraction, which is given as 2 d sin theta equals n lambda. Here d is the interplanar separation distance, theta is the angle of incidence, let me say angle of scattering, and lambda is the wavelength of the incident X-rays. N is any integer. Corresponding to different values of n, diffraction maxima will arise. We will now try to see how this comes about by calculating the amplitude of the diffracted waves from all the atoms at a point when a wave is incident at one of the atoms, as shown in this figure. So, you have an X-ray of wave vector k 0 incident X-ray. It defines the direction, the magnitude is 2 pi by lambda, where lambda is the wavelength, and the direction is along the direction of propagation. Of the wave. And now k dash is the scattered wave vector of the scattered X-rays. So, we are considering a small volume element at a point r prime scattered by atoms in a small volume around at position vector r prime. Now, if I consider the point at which we measure the scattered amplitude is, if it is taken, if the point at which scattered X-ray amplitude is calculated is given by the position vector r, and if this is sufficiently far away from the arrays of atoms which do the scattering, then we can assume that the secondary wavelets of Huygens theory, which originate from the scattering atoms, may the spherical wave fronts of these secondary wavelets will become plane waves at sufficiently large distances, and these plane waves can be written as exponential I k dash dot r minus omega t. The amplitude of the wave as it leaves the atom at r prime, the incident amplitude is proportional to exponential I k 0 dot r prime minus omega t. This is the incident amplitude at the atom located in R. So, we have a situation where we can easily calculate the amplitude at the observation point. The amplitude at the observation point of the scattered wave is proportional to, or we can write it as some a exponential I k naught dot r prime minus omega t. This we will write later, times exponential I k dash dot r minus r prime, that is the distance between r and r prime, times exponential minus I omega t. So, that would be the amplitude. So, this can be written, rewritten as a exponential I k dot r times exponential I k naught minus k prime dot r. R prime. This is simply neglecting, omitting the time dependent term. So, this is simply rearranged in this form. So, this is the amplitude when we drop out the time dependent. The total amplitude is got by summing over all the atoms. So, the atomic terms are here. So, this is a summation over all atoms, that is the total amplitude. So, that can also be rewritten as a e to the power I k dot r integral all atoms, since we are having atoms which are practically continuously distributed. So, we can write a scattering amplitude times exponential I delta k dot r prime, where delta k is just this quantity. This is, I write it as delta k. So, this is a, this f of r prime is a periodic function depending on the distribution of atoms. So, it has a maximum value at the site of a lattice point, it is unity and it is 0 everywhere else. Wherever there is an atom, there is a scattering amplitude. So, it has this has, which has the same periodicity, is the same as that of the crystal lattice. So, it has the same thing. Therefore, this amplitude will be non-zero only when this exponential term does not vanish. In other words, the condition for a diffraction maximum is got as delta k dot r equal to n into 2 pi, where n is an integer. This is known as Laue condition. This was first written by Max von Laue. Well, I will write to just keep the notation, I will keep the r prime. So, this is the condition for constructive interference or reinforcement of the scattered amplitudes, so that there is a Bragg reflection. So, strictly this leads to a Bragg reflection. We can write this condition in component form, because this is a vector equation. So, we can write it in component form. So, if we do this, we get three conditions in terms of integers which are 2 pi by a multiples of 2 pi by a, 2 pi by b, 2 pi by c for a lattice with periodicity of a, b and c in the three mutually orthogonal crystallographic directions. So, it is now useful to construct a lattice with unit cell with lengths of this, and such a lattice is known as a lattice with unit cell of dimensions 2 pi by a, 2 pi by b, 2 pi by c is known as the reciprocal lattice. In crystallography, this is a very useful concept, the concept of a reciprocal lattice. It is called reciprocal lattice because it involves a unit cell whose lengths are the reciprocals of the three lattice parameters. So, we can write the basis vectors of such a reciprocal lattice. If a, b and c are the lattice vectors of the original lattice, reciprocal lattice vectors are given by a star equals 2 pi times b cross c by a dot b cross c, b star is 2 pi times c cross a by a dot b cross c, and c star is 2 pi times a cross b by a dot b cross c. So, we define the reciprocal lattice vectors in this way, and a vector which connects 2 points in the reciprocal lattice is known as a reciprocal lattice vector. A reciprocal lattice vector is usually denoted by the symbol G. So, the condition for maximum then becomes delta k equals n dot G. Since diffraction takes place, diffraction means it is elastic scattering. What is elastic scattering? Elastic scattering is a scattering event in which the energy is conserved. Apart from momentum conservation, energy is also conserved in the sense that the incident and scattered wave vectors will have equal magnitudes and differ only in direction. So, delta k will have a magnitude equal to 2 times k naught sin theta. So, if you plug this in, where theta is the scattering angle. So, we get 2 times sin theta equal to n into 2 pi. And we can show that the interplanar spacing is just 1 by G. Therefore, we arrive at the Bragg condition 2d sin theta equals n lambda. So, we see that the Laue condition and the Bragg condition for diffraction maximum are really one and the same. Because the interplanar spacing in all crystals is of the order of d is of the order of a few angstroms. Therefore, X-rays which have the wavelength of the same order or smaller are commonly used to observe the diffraction of waves in solids. The technique of determining the structures of crystals using X-ray diffraction is known as X-ray crystallography. X-ray crystallography gives you the basic principles governing how to determine crystal structures using X-ray diffraction. There are several methods. We will discuss a few of them here. The first one is known as the Debye-Scherrer method. This is the most popular and most commonly used method. So, I am discussing that first. So, the first method is known as the Debye-Scherrer. This is also known as the powder method, since it uses samples in the form of powder method. So, you have a sample in the form of a powder or polycrystalline sample. That is why it is very popular, that you do not require a crystal. You can take any solid in the form of a polycrystalline or powder sample. So, you do not have to take special efforts to grow a single crystal. So, you have a large number of tiny crystals oriented in all possible directions randomly with respect to the incident X-ray direction. Wherever you apply the incident X-ray direction, the crystal grains will be oriented in all possible directions isotropically, because there is no way of saying which way it will be preferentially oriented. So, all grains will be oriented randomly around the incident direction, whatever be the direction. So, when a monochromatic X-rays, we use a polycrystalline sample and monochromatic X-rays, that is X-rays of a definite wavelength. So, these are the two ingredients in the Debye-Scherrer method. When you have a monochromatic X-ray beam which is incident on such a polycrystalline sample, Since the grains are oriented in all possible directions, Bragg reflection takes place. Almost all the planes, because you have a large number of grains oriented in all possible directions. So, some plane or other will satisfy the Bragg law condition. So, for every set of HKL planes containing different HKL planes, HKL are the Miller indices of the crystallographic planes. So, for every set of, there are different planes with different values of HK and L, the Miller indices. So, there will be several grains in the powder sample which are oriented in such a direction as to satisfy the Bragg condition for the given incident X-ray. So, you take the sample in the form of very fine powder, which is usually put inside a thin glass capillary tube or is attached to a glass fiber by coating the glass fiber with grease and then rolled in the powder. Then this is mounted at the center of a cylindrical camera, which is shown, that is known as the Derbyshire camera. It is shown in the next figure. So, that is the Derbyshire camera, and you see the sample mounted at the center. A strip of photographic plate is positioned inside the camera around the inner wall. So, you have a strip positioned around the inner wall of this camera. So, there is a photographic film. In the middle, such that the film surrounds the sample. The camera has a hole for the incident X-ray and a diametrically opposite hole for the outgrowing X-ray. So, there is an entrance for the incident X-rays and an exit. So, that is the basic details of the Derbyshire camera. When the monochromatic X-ray beam falls on the specimen, the incident beam undergoes Bragg reflection from the various crystallographic planes. So, the rays reflected from one set of HKL planes, making an angle theta with the incident beam, will all lie on the surface of a cone whose apex is at the point of contact of the incident radiation with the specimen. This is shown in the next figure, where how the X-ray diffraction pattern is formed is shown. So, the incident X-ray beam is coming, and then all the points situated on that cone will correspond to the same Bragg reflection condition. So, the diffraction beam from two sets of planes is shown in this figure. So, from this figure you can see that the solid angle subtended by the cone is 4 theta. So, each set of planes for a given specific SHL value gives rise to such a cone of reflected rays, and therefore, these cones intersect the cylindrical photographic plate in circles as illustrated in the next figure. So, these cones intersect the photographic plate. So, you have the diffracted X-ray beam from the powder sample intersects the photographic plate. So, you get each cone generates a pair of arcs on the photographic plate. The arcs are positioned symmetrically with respect to the central hole. There will be several such pairs. So, those will be different pairs of arcs, each corresponding to one set of HKL planes. So, this is how a typical record will show. Powder diffraction pattern will be formed on the photographic plate as shown in the figure So, this is quite simple. This picture that is shown in this figure is a very simple one, because it corresponds to a simple monatomic cubic crystal. If the crystal structure is complex, this pattern also will become more complicated with closely spaced arcs of varying intensities. So, how to interpret the X-ray pattern? It is easier for simple cubic structures. So, this such a simple description of how the crystal structure can be determined using the diffraction pattern generated by a simple monatomic cubic lattice is shown in this figure, is described now. So, if you have a cubic crystal, then the condition is, we already saw this, mentioned this in an earlier lecture, where A is the lattice parameter for the cubic of a cubic lattice, cubic solid crystal. DHKL is the interplanar spacing corresponding to a set of HKL planes, where HKLs are the Miller indices. So, substituting this value in the Bragg's law, we get sin square theta, and rearranging the terms, you get n square lambda square h square plus k square plus L square by a square 4a square. So, that is the basic equation. So, the lambda is fixed in a given X-ray experiment. The unit cell parameter is fixed for the given solid. N is the order of the diffraction, so which takes integer values. So, we can see that sin square theta is proportional to h square plus k square plus L square. Everything else is fixed. Now, the Bragg angle is related to the distance between the arcs. This distance is what is measured, and this is given by the solid angle is 4 theta times r, which is the radius of the camera, gives you this distance. So, you can measure this distance, and knowing the angle of scattering and knowing the radius of the Debye-Scherrer camera, the distance from the distance which is accurately measured from the diffracted pattern, we can calculate the theta values using this equation. So, the sin square theta is calculated. Then, if it is tabulated, the common factor between the different values of sin square theta gives you lambda square by 4a square. So, what do? You write down calculate the sin square theta and then find the common factor. For example, table shows the different HKL planes and the corresponding h square plus k square plus L square. So, we can calculate the common factor lambda square by a square, and hence find the lattice parameter A. Now, we will also see that for a given lattice type, Bragg reflection is possible only from certain HKL planes. This is known as the extinction rule. This simplifies the analysis of the X-ray diffraction pattern. Not all values of HKL give rise to a Bragg reflection. So, depending on the given lattice type, Bragg reflection occurs only from those crystal planes which satisfy certain conditions on the HK and L values. This is, to understand this, we have to write down what is known as the structure factor. which is really determined for a given HKL planes as sigma over j Fj. Fj is the scattering amplitude times exponential I 2 pi into h xj plus k yj plus L zj. So, that defines the where xj, yj, zj are the coordinates of the jth atom, which lies on a crystal lattice plane whose Miller indices are h, k and L. So, once you have this summation over j is over all such identical atoms in the unit cell. Fj is known as the atomic scattering factor. Let us now evaluate this structure factor. This structure factor goes into the intensity of the diffracted beam. So, if you take a simple cubic structure, a simple cubic solid, it has atoms at the corners of this cubic unit cell, which is primitive. So, there is only one atom per unit cell. You may wonder, there are 8 atoms, why do I say there is only one atom? You must remember, this unit cell is surrounded by other unit cells in all the 3 directions on either side. Therefore, all these 8 atoms are shared by these adjacent atom unit cells as well. So, there is only 1/8 of an atom which contributes to a given unit cell, and since there are 8 atoms at the 8 vertices of a cube, 8 times 1/8 gives you 1. So, that is really the only one atom in the unit cell which is at 0 0 0, the origin. We take this atom at the origin. So, SHKL, substituting in that expression, is just F, because the summation is just over one term. So, it is non-zero, the structure factor is non-zero for any sets of HKLs. So, all the crystal planes give rise to Bragg diffraction. So, there is no extinction role really, but come to a body centered cubic lattice. A body centered cubic lattice has 2 atoms per unit cell, one atom at 0 0 0 and another one atom in the body center of the cube, which is half half half. It is at the distance of half the lattice separation, the distance between consecutive atoms. So, substituting this, you get SHKL equals 1 plus F times 1 plus exponential I pi, the 2 pi cancels with the 2 factor 2 cancels with the 2 in the denominator. So, I get H plus K plus L. So, that will be the scattering amplitude. So, this will be non-zero only if H plus K plus L is even. Only when this is an even number, this leads to exponential I pi times 2 or 4, otherwise it becomes 0. So, only even values of H plus K plus L, the sum of H, K, L should be an even number. That is the extinction rule for a body centered cubic lattice. Going on to a face centered cubic lattice, we see that there are 4 atoms in the unit cell. Cubic unit cell, one at 0 0 0, then one at 0 half half at the face center, one at half 0 half, and another at half 0. These are the coordinates of the centers of the faces. So, the SHKL in this case is going to be f times 1 plus exponential I pi into h plus k plus exponential I pi into k plus L plus exponential I pi into L plus h. So, the structure factor will be non-zero in this case only when this will be non-zero only when h, k and L are all odd or are all even. So, that is the extinction rule for a face centered lattice. So, these 3 extinction rules are summarized here in the next table, and the next table, as I showed you already, lists the different h plus k plus L values and the corresponding h square plus k square plus L square values for these combinations which enter into the Bragg condition. From the above and the extinction rule, it can be concluded that the possible ratios of h square plus k square plus L square values for the simple cubic, body centered cubic and face centered cubic structure, these are shown in the next table. So, the ratios of h square plus k square plus L square corresponding to different HKL values for which Bragg reflections are allowed. For the case of a simple cubic, the ratio is 1:2:3:4, everything, all the numbers. For a body centered cubic lattice, it is 2:4:6:8:10, which can be reduced to 1:2:3:4, etc. And the face centered cubic lattice, it is only 3:4:8:11:12:16, etc. So, you see how there are 6 systematic extinctions. So, the experimentally calculated ratios, knowing these h square plus k square plus L square values, you can calculate the ratios of sin square theta values, and so we can compare the h square plus k square plus L square values and the sin square theta values. The lattice type is immediately found by matching these ratios. So, that is how the analysis is done for the Debye-Scherrer method. The next method that we talk about is the Laue method. In this technique, this is the second method. The first method was the Debye-Scherrer method. In the Debye-Scherrer method, we use monochromatic X-rays. Here we use continuous or white X-rays, not monochromatic X-rays. And in the Debye-Scherrer method, we use a polycrystalline sample, but here this specimen is in the form of a single crystal specimen. So, the diffraction pattern will be a set of spots where there is maximum of diffracted intensity. The arrangement of these spots indicates the symmetry of the crystal with respect to the incident X-ray direction. If the X-ray direction beam is directed along a n-fold rotation axis of symmetry, the diffraction pattern will then display the symmetry of the n-fold axis. So, the crystallographic directions in a crystal can be identified using the Laue method. So, the next figure shows a Laue pattern for a single crystal of ammonium chloride. So, you see how the diffraction spots are distributed. The third method goes by the name the Bragg diffractometer. This is the bread and butter of every X-ray crystallographer. This is used for the determination of crystal structure of materials, and the next figure shows the experimental arrangement in a diffractometer. You have the schematic diagram is shown with a monochromatic X-ray beam incident on a single crystal, and then the diffracted beam is seen by in terms of using an X-ray detector mounted on a rotatable arm. The diffraction so, the X-rays get Bragg reflected from various crystal planes in different directions. The X-ray detector shows a peak at those angles at which the Bragg's law is satisfied by a set of crystal planes. So, such a diffraction pattern for iron is shown in figure. Can see the diffraction maxima, the Bragg diffraction maxima corresponding to the different HKL planes, when the intensity of the scattered X-rays is plotted as a function of the diffraction angle. So, we have now considered all the important techniques of X-ray diffraction. In addition to X-rays, we can also use a beam of electrons or a beam of neutrons. These are particles which can again get scattered, and you can have electron diffraction or neutron diffraction.